So we're now going to discuss why tails of infinite series are important, how they help us when we try to look at examples. So first of all, what do we mean by a tail? Well, if we have an infinite series ak where we sum from, say, 0 to infinity, we can split this up into its nth partial sum like this, and what remains is what we call its nth tail. So k is equal to n plus 1 to infinity like this. So this would be the nth tail of this guy. And this thing here is, of course, the nth partial sum. And since tail begins with a t, perhaps we should call this Tn. An important proposition, or a proposition that explains to us why we should care about tails, is the following. So for all k in n, and I use capital K here because that's what I do in the lecture notes for the course. I could use n. We have that your original series here converges if and only if the kth tail converges here. What does this mean? Well, this basically just means that in order to figure out if my series converges, I can choose any k that I want, and then I can consider this tail here. And if I'm able to prove that this tail converges, then my original guy does so. Intuitively, this is not so strange. So let's say that k is equal to 10 here. Now what's the difference between these two expressions? Well, here I'm summing from the terms starting from index 0 and onwards. In here I'm just dropping the 10 first terms, or 11 first terms if I'm starting to count to 0 here. And any finite number of first terms, well, they will just sum up to something finite. So it doesn't matter if I leave them out or not. So the point here is that the k is fixed. So how to prove this? So proof, well, let's express the partial sums involved here. So the partial sums of this guy, let's call them ANs. And let's call the partial sums of these guys BNs. And now, in order for the proof to look pretty, to be easy to express, we're going to define these in a slightly special way, in such a way that A0 is A0, A1 is A0 plus A1, so nothing special here. But here, we're going to say that B0 is 0, B1 is 0, and all the way down to BK, whatever he is 0. And then bk plus 1 is equal to ak plus 1, and then bk plus 2 is equal to ak plus 1 plus ak plus 2, capital K's here everywhere, like this, meaning that these partial sums are 0 until we hit the first non-zero term here, because I want the indices here to match in a good way. What does this give me? This means that an, when n is bigger, strictly bigger than capital K, well, is equal to what? So here, if I move all the way down here, so I'm getting here, let's start at ak plus 1. So he will be a0 all the way to ak, and then ak plus 1, like this. If I do ak plus 2, I'm just adding an extra term here. And we can see that these guys here, that's going to be my ak, and this guy here, well, that's my bk plus 1. So here I can write this as ak, and then plus b, and I use the same index here as here. So I'm getting bn there. And notice that this is not really true when you take n smaller than capital K, because, well, sure, these guys become a 0, but this guy doesn't change. So notice that this thing here is fixed, okay? And so what happens? Well, if I now do the limit of the ANs, I'm wondering what they tend to. This is the same as if I'm taking the limit as n goes to infinity of AK and BN, but this AK don't move. It's a fixed number. We fixed it up here somewhere. So here, nothing happens to him. So this thing here is just equal to the limit as n goes to infinity of the bn's. And then the thing is, if this converges, and if this converges, this converges. Because as I said in the beginning, when I tried to explain this intuitively, the only thing that's different between these two sequences of partial sums is a fixed constant. And that ends the proof. So let's now do an example where we use this thing of looking at tails. So the example we're going to look at is the sum of k divided by square root of k to the 5th plus 1. And here we can safely start at 0. Well, we're not really going to use this tail result as a backdrop for our intuition. So if we now do the intuitive step here, well, we can start out by using the proposition. So convergent, if and only if the sum starting at, well, let's do, I don't know what this is a million, okay? So if and only if the sum where we start at a million converges, okay? And here we have a 5. But what can we say about this? Well, if I take a million to the 5th and I add 1, the 1 is not going to amount to much. So now I'm doing the intuitive thing. This is not rigorous, but I'm going to rigorize it soon. So then I start at a million here. I go to infinity. Now I have k to the 5th here, okay? And this I can simplify. So here, let me not bother to write out the summation limits, but I have k divided by k to the 5 halves. This means I have 1 over k to the 3 halves here, okay? And this thing here converges because this is a so-called alpha series where the exponent here is strictly bigger than 1. So intuitively, we expect this thing here to converge because the terms for large k will behave like k to the 1 over k to the 3 halves. So let's now do the formal step to prove that our intuition is correct. So what we do then is try to use the comparison theorem. But now we know that we're after an inequality connecting these terms to those terms. And in this case, this is not so hard to do because if we replace the 1 by a 0, this expression becomes larger. So we're getting this. And now, just as I got 3 halves in the power above, I'm getting it now. So we have this. So by comparison tests, by the above inequality, we have that the sum k goes from 1 to infinity. So I can take, I mean, I can start wherever I want. I shouldn't start at 0 because I have him here. Implies that the sum k from 1 to infinity converges, implies this converges. And if I want, I can use this tail result to say that then, well, this thing here converges. And of course, now we realize that if I have k equal to 0, then this is 0. So, I mean, nothing happens. So here you don't change anything if you just write 0 here. And then we're done. So the main point here is that knowing that we can always pass the tails can be a really powerful tool in figuring out how the terms of this sum really act like when k is starting to get really, really big, and to understand that this is something we can use in a good way.